Hello everyone, and thanks for watching Edupedia World videos. In this video we'll add another form in which we can solve equations, which is relative motion. Up till now we have 5 things we need to keep in mind. We need to know between which two events are we applying the equation. We need to be aware of which equation to use, which is often decided by the fact that once we know 3 out of the 5 unknowns, we can find the other 2, and based on which 3 we know, we can know which equation to use. Of course, they're only valid if the acceleration is constant, and in the last lecture we saw that it's also important to know in which direction are we applying the equation if we are solving problems for motion in a plane. In this lecture in relative motion, we'll just add one more concept to this, which is you need to be sure of in which frame are you applying the equation. So we see that we are incrementally increasing our knowledge of kinematics step by step. Let's look at that in a little bit more detail. So I'm going to show you how we can solve the same problem in 2 separate frames, right? The first thing to know is that motion is always relative. It doesn't really make sense to say a body is at rest or a body is at motion. You could say, for example, that a table in your room is at rest, but it's not really at rest if I'm standing on the moon and looking down. In the frame of the moon, everything on the earth is moving. It's not stationary, right? But in the frame of the earth or in the frame of your room, the table is stationary. So when we say something is stationary or something is moving, we always mean relative to us, that is relative to an observer. And relative to different observers, different motions can look differently. For example, let's say there's a car moving towards right with a speed of 10 meters per second. There are 3 people. One of them is standing. The other one is moving forward with 1 meters per second. And the third one is moving towards left with a speed of 1 meters per second. So the person who's stationary will see the speed of this car to be 10 meters per second. But the person who's running in the same direction, by the time the car has covered 10 meters, the person has covered 1 meter. So the person will see that the car has only traveled 9 meters forward. So he'll see the speed to be 9 meters per second. And the person who's going in the backwards direction will see the speed to be 11 meters per second. Let's look at that a little bit more concretely. Generally, we represent a frame of reference by a coordinate axis. So to represent 2 frames of reference, I'm going to draw 2 separate coordinate axes. Let's say this is a frame S which has an origin O, and let's say this is another frame S dash which has an origin O dash. And let's say there is a point P. To represent the position of the point, we use something called a position vector. The position vector is just simply the vector starting from the origin and towards that point. So the position vector of P in the frame S would be this vector OP. And the position vector of P in the frame S dash would be this vector O dash P. Right? And the position of the origin of the frame S dash with respect to the frame S would be this vector O dash. O dash is the position of S dash, in fact of the origin of S dash with respect to the origin of S. But the terminology we often use is that O dash is the position of S dash with respect to S. When we say the position of a frame, we generally mean the position of the origin of that frame. Right? By triangle rule, we can easily see that O dash, the vector, plus O dash P, the vector, is equal to OP, the vector. Another way to write this would be O dash P is equal to OP minus O dash. right? But what is O dash P? O dash P is the position vector. Position vector is generally referred to by R. O dash P is the position vector of P in the frame S dash, right? And what is equal to? It is equal to the position vector of the frame, or position vector of the position P in the frame S, which is OP, minus the position vector, again R, of O dash or S dash with respect to S. When I am writing vector of A slash B, a vector alpha, it could be anything, position, velocity, acceleration, of A with respect to B, it means of A relative to or with respect to B. So R of P slash S dash is just another way of writing the position vector of P in the frame S dash. That is equal to the position vector of P in the frame S minus the position vector of S dash in the frame S. This is the holy grail. This is the formula from which we'll be able to solve every question related to relative motion. And this just says the position of P relative to S dash is the position of P relative to S minus the position of S dash relative to S. An easy way to remember this generally is a vector R or a vector V or a vector A or a vector U or a vector S. It doesn't matter. Right now we're just talking about vectors. Of A with respect to B is simply R of A minus R of B. That's the easy way to remember it. But of course, R of A doesn't make any sense. I just told you position is always relative to a frame. So these both can be, in fact, have to be relative to another frame. C could be any frame, it doesn't matter. Instead of C, we could use D, and the two RC minus RD in these would cancel. Right? So the position vector of A relative to B is simply the position vector of A minus the position vector of B. We can differentiate this to get other results. So right now we saw that R of A with respect to B is R of A minus R of B with respect to a third frame C. Now if we differentiate this equation with respect to time, that means to the whole equation we do d by dt of it. What that says is d of RA with respect to B by dt is equal to d R of A with respect to C by dt minus d R of B with respect to C by dt. How do we differentiate a vector? We simply differentiate its components. We've seen that earlier. So what this gives us is V of A with respect to B, that is the velocity now, is equal to V of A with respect to C minus V of B with respect to C. Differentiating it further gives us the acceleration. A of A with respect to B is equal to A of A with respect to C minus A of B with respect to C. Right? So this is the basic concept which is used in all of relative motion. That position or velocity or acceleration or any vector of A with respect to B is the vector of A minus the vector of B. Of course, it's all relative, so both of them have to be taken relative to a common frame C. Right? Let's see how to apply this in some problems now. Let's say we have two particles A and B, which are at a distance of 30 meters from each other. A starts towards B with a speed of 4 meters per second and acceleration of 2 meters per second square. B starts moving towards A at the same time with an initial velocity of minus 6 meters per second. I say minus because it's moving in the negative x direction, and an acceleration of minus 3 meters per second square. And we want to find out after how much time do they meet. I'm going to solve this question 3 ways. The first, in the ground frame, the second in the frame of A, and the third in the frame of B, and I'm going to show you we get the same results no matter how we solve the question. So the first we'll do it in the ground frame. In the ground frame, they both meet when the total distance covered by them becomes 30. The distance covered by the first body, that is the body A, would be ut plus half at square. That is 4t plus half into 2 into t square. The distance covered by the second one would be 6t plus half into 3 into t square, but all of it in the negative direction. So the second one would be minus 6t minus half into 3 into t square. So this is the distance covered, displacement covered by the first. This is the displacement covered by the second. Now we need to reverse the second displacement, and we need to add it to the first, and that should give us 30 meters. And when that is true, that is when the both particles will have collided. So we subtract these two and make it equal to 30. So that gives me 4t plus half into 2t square plus 6t plus half into 3 into t square, and this should be equal to 30. Okay, I'll remove it now. So this gives me 10t plus half into 5 into t square is equal to 30. Upon solving, this gives me 20t plus 5t square is equal to 60, or if I cancel 5, it gives me t square plus 4t minus 12 equals 0, which gives me t plus 6 into t minus 2 equals 0, which gives me t is equal to 2 seconds. That means they collide after 2 seconds. So now I'll try to do the same thing, but from the frame of A. I'm not going to solve it completely, I'm just going to show you that in the frame of A the equations are the same. So in the frame of A, u of A is u of A with respect to A is simply u of A minus velocity of A, which is 0. You can see that directly. If you are in a car, the speed of the car relative to you is 0 because you are at the same speed. The speed of the earth relative to you, or the speed of the trees on the road relative to you, would be some negative value, but the speed of the car relative to you, or the speed of you relative to you, is 0. Similarly, the acceleration of A is also 0. U of B now is, so u of B with respect to A will be u of B minus u of A. U of B we know to be minus 6 minus u of A, that is minus 4, which becomes minus 10. Similarly, A of B, these are both with respect to A, by the way. These are all with respect to A. B of A, acceleration of B with respect to A will be acceleration of B minus acceleration of A. That is minus 3 minus 2. That is equal to minus 5. And this, the equation which will give us in the frame of A, is the displacement of B should be minus 30. When B travels negative 30 meters, it reaches A. So the equation will be minus 30s is equal to ut, that is minus 10t minus 5t square by 2. And you can see this equation is basically the same as the equation in this place, except both of them are reversed by a minus sign. So we see that in the frame of A, we get the same equation. In the frame of B, u of B with respect to B is obviously 0, and A of B with respect to B is 0. U of A with respect to B is u of A minus u of B. U of A was 4 minus u of B. U of B was minus 6. Be care to take of the signs. Make sure you take care of the signs. There's a lot of error students doing that. So this will give us 10. Similarly, the acceleration of A with respect to B would be 2 minus minus 3, which is equal to 5. And with respect to B, when A travels 30 meters, it will collide with B. So the equation will be 30 is equal to 10t plus half into 5 into t square. We see that again the equation is same, which will give us the same result, t is equal to 2 seconds. So again, I show you that we can solve any question in any frame. Of course, we would have gotten an error if in an equation we used half terms in the frame of A and half of the terms in the frame of B. So whenever we are applying an equation, we need to make sure every term in that equation is relative to the same frame. Which frame? That doesn't really matter, as the answer will always be same, right? So some applications of these problems involve problems with rain and how we see the rain falling. So we know that from common sense that if rain is falling vertically downwards and I run forwards, then I'll see the rain falling in this direction. We've all had that experience. So what happens is, this is, let's say, V of the rain and this is V of the man. So V of the rain with respect to the man is equal to V of rain minus V of man. And we see this is the direction of V of rain. If this is V of man, then the opposite direction will be minus V of man. And this vector added with this vector thus give us this vector. So this is how the concept of relative motion applies to rain. Let's see a concrete example. We are given that rain is falling down at an angle of 45 degrees with the horizontal with a speed of 10 meters per second. This is V of rain. And let's say a man is running with a speed V, let's call it U for simplicity, such that the rain appears to fall vertical. Okay, so the rain is actually falling at an angle, but I want to run at such a speed such that relative to me the rain seems to fall vertically. So with what speed U should the man run? So this is easy enough. Velocity of rain with respect to the man will be velocity of rain minus velocity of the man, right? This is the velocity of the rain, 10 meters per second at an angle of 45. If this is the velocity of the man U, then the negative of the velocity of man will be minus U, right? So this will be minus U. The sum of these two will be the velocity of the rain with respect to the man, and we want that to be vertical. So we want the sum of these to be vertical. If U was smaller, this would be at an angle towards the right. If U was larger, the magnitude, this would be towards the left. But we want this to be vertical, and we can do that by actually solving it, or we can just look at the triangle. If this is 10, this is 45, this should be 10 by root 2. So if I am running at a speed of 10 by root 2 meters per second, the rain will appear to me to fall vertically. Right. These are some examples of relative motion. In the next class, we'll start discussing the kinematics of circular motion. Thank you.